Alright guys, we're going to be looking at some matrix enlargements today. Bit of a shorter video than before because I wanted to put the first two bits of the chapter together just to make everything a little bit easier because there's not a lot going on in exercise 7a. So this is a unit square as familiar from before, and what we're going to do is we're going to enlarge it by a scale factor of 2. So if I enlarge it by a scale factor of 2, you should notice, hopefully, that the corners will now be at these positions. So 2, 0, 0, 2, and of course 2, 2. So similar to before, we can take this corner and this corner and use those to write out our matrix for the transformation. So the coordinate on the x-axis has been stretched along to 2, 0, so the column of the matrix would be 2, 0, and the y-coordinate, the coordinate on the y-axis has been stretched upwards to 0, 2, so we get this. Okay, and that is a matrix representing the transformation enlargement scale factor 2. So doesn't take a great leap to work out that this would be the matrix representing an enlargement scale factor k. So that's that. That's quite simple. If you get given a matrix like this where it was 3003, what transformation is this? Enlargement scale factor 3, centered on the origin. Okay, the enlargements will always be centered on the origin. So there you have it with that. We're also here to look at a slightly different type of transformation called a stretch. So a stretch is different to an enlargement. You may have been told off once or twice by your GCSE teacher for writing like stretch or something like that instead of enlargement when you were doing your GCSE work, but now we do want to know what a stretch is. So if I have a unit square again, like this time I might want to stretch it. So rather than enlarging in the same scale factor in every direction from the origin, I might only want to enlarge, for example, parallel to the x-axis by scale factor 2. So I've stretched this in the x direction. And this coordinate here, the 1, 0, has moved to 2, 0, the 1, 1 has moved to 2, 1, but the 0, 1 has stayed in the same place. So 2, 0 and 0, 1 are where the important corners that tell us the matrix have moved to. So 0, 1 is actually not moved, 2, 0. So 2, 0, 0, 1 is a matrix that would represent this transformation, a stretch parallel to the x-axis, scale factor 2. So that's got, just getting too excited with my L's there. So stretch parallel to the x-axis, scale factor 2. Okay, so I could write the matrix K0, 0, 1 for a stretch parallel to the x-axis, that would be scale factor K. So any general stretch parallel to the x-axis would be represented by this matrix. So if I had the same thing, but this time I'm going in the y direction, so I'm stretching parallel to y. This time the coordinate that was on the x-axis stays in the same place, and the coordinate on the y-axis moves to 0, 2. So it would be the same kind of structure of matrix, but this time it would be 1, 0, 0, 2. And that would be a stretch parallel to the y-axis scale factor 2. So we can infer from that pretty simply as well that if we have 1, 0, 0, k, that would be a stretch parallel to the y-axis scale factor k. So these are just two different ways of writing, two different types of stretch. You can have them both in one go. So here's a quick example. This is like one transformation that stretches in both directions. Describe this transformation where it's not an enlargement because the leading diagonal isn't the same. So this would be a stretch scale factor 3. So stretch scale factor 3 parallel to the x-axis, and also a stretch scale factor -3 parallel to the y-axis. So it's both of those. Quick example with the determinant. So using a determinant, we can also use the determinant when we're doing enlargements. So the determinant is the scale factor of an enlargement or transformation generally, I guess we should say, because it's not necessarily a transformation, an enlargement, sorry. So it's the scale factor of a transformation. Quite an easy to use fact, to be honest. So we have, for example, this question, question B. Question A is easy, determinant M is 0. Question B, R is transformed into S by transformation T, which is represented by this matrix M. Area of S is 63 square units. So, well, let's think, first of all, what's the determinant of M? Determinant of M is 4 times minus 7 minus 2 times minus 5, AD minus BC. So that's going to be minus 28 plus 10, which is minus 18. So scale factor is negative, doesn't really matter. Like, if you'll know from like negative enlargements, it's kind of not actually saying, the negative just means it's kind of flipping to the other side of the center of enlargement. So the scale factor here is essentially just 18. Okay. So the scale factor is 18. S is 63 units. S is the result. Okay, S is what this triangle is transformed into. So the triangle is transformed into the triangle S. So the result is that we get a area of 63. So we need to actually divide by 63 to find out the original area in this case. So 63 divided by 18, which is 7 over 2. So that's the area of the original triangle, 7 over 2 square units. Show that the line y equals 2x is invariant under the transformation t. So invariant just means that essentially it maps onto itself. Okay, so it maps onto itself. So if I take any point on the line y equals 2x, it should transform onto the line y equals 2x. So you might want to just stop and have a quick think about how you could show this yourselves, and then I'll show you my solution that I've done. So you might want to pause the video here and have a go at it. I'm going to go straight onto here where I've got the solution written out. So if I take a coordinate on the line y equals 2x, any coordinate on the line y equals 2x is going to be of the form x 2x. So if I take the point x 2x and I multiply it by 4 minus 5, 2 minus 7, I get this result, which is minus 6x minus 12x. That is still on a line y equals 2x. Okay, because minus 12x is equal to 2 times minus 6x. So the y coordinate here is double the x coordinate. It's still on the line y equals 2x. You could also show this by factorising negative 2, which would give you x negative 2. But you could show this by factorising negative 6, which would give you x 2x again. So it's the same line, it's just being kind of scaled along. Okay, so it's invariant, it maps to itself. Exercise 7c, crack with the exam questions. Those are going to be the most important ones. It's not too difficult, this topic, but you do have to make sure you practice so you don't make silly mistakes.